Hello everyone, this is problem number 3. Um, we're given this figure right here, and it says that the bent rod is supporting at bearings C and D and the wire AH. The portion AB of the rod is 250 millimeters long, and W is equal to 540 newtons. Assume the bearing at D does not exert any axial thrust. That's an important sentence right there. So let's go ahead and draw a free body diagram. So I'm just going to draw a head on this picture again. So we see that A to H is tension. So I'm going to label that TAH. We know that C is a bearing that does not allow the rod to move at all. So we have a CZ component, CX component, and a CY component, like so. And we also know that D is the same bearing as C, but it does not exert any axial thrust. And what that means is basically you have this point D right here, and along its axis is this rod. And because it's exerting no thrust, it basically is saying that D of X is equal to 0 newtons. So we don't need to include that in our free body diagram. Therefore, we only have a DZ force and a DY force. And that's our entire free body diagram. So now part 2 of the question is asking for the tension in wire AH. And what we want to do to solve for it is first we want to label all of our points. And because our point at C has the most unknowns, which is 3 unknowns right here, we're going to want to take the moment about C to negate all those unknowns. And then we'll be able to solve for 3 cross products, the one of tension right here, the one of the weight, and the one of D. And that will give us the answer that we need. So I'm going to go ahead and label our direction vector from C to H, and that is equal to negative 50I plus 250J. We have our position vector from C to D, which is equal to 300I, and this is just along the rod, like so. And we have our position vector from C to F, which is equal to 350I plus 250K. So if you want to go ahead and check those values, you can. Remember that the tension from A to H is equal to the magnitude times the unit vector from A to H. So you'll also need those components as well. But what we can do, because T of H is only acting in 2 axes, the y component and the z component, we can break it up into its sine and cosine angles. But this method is also viable to solve for tension. But using trigonometry, we'll get that the vector t is equal to its magnitude times sine of 30j, this is in degrees, minus t cosine of 30 in the k component. All right, and to simplify that further, we just get t times 0.5j minus 0.866k. And I got that by just plugging into my calculator. And so now we have all the information we need to solve this problem. So we take the moment about C, set it equal to 0. And that equation that we're doing is, I'll draw it out right here on the free body diagram. So we're taking the position vector from C to H, because that's where the force of tension extends. So we're connecting this direction vector with this force vector right here. We're taking from C to D to connect to these two forces right here. And we're taking from C to F to connect to this weight force right here. So those cross products look something like this. We have our I JK component, negative 50 in the I, 250 in the J, and 0 in the K, and then we have 0, 0.5 minus 0.86, and multiply it with tension. Then we're going to add that, I, J, K. We have 300 in the I. This is for our D forces. So we have 0 in the X component for D, and then we have dy and dz. Then we have our last cross product, which is for the weight, I, J, K. We have 350 in the I, 0 in the J, and 250 in the K value. We have 0, negative W, and 0. And we set that equal to 0. All right. Then we can solve for these. So the way you solve the cross product, in case you need a refresher, is you cover up this, multiply these two entries with those two, or sorry, multiply these two entries and then subtract them with this. So because there's a 0 here, it subtracts with 0. So your I component will just be 250 times negative 0.86. All right, and then you can repeat the same process for the middle value for the J component and then for the K component. And then you'll break up the components into its separate equations, which are, we have the I component equation, which is negative 216.5t minus 135,000 equals 0. J is equal to negative 43.3t minus 300 dz is equal to 0. And we have our K equation is negative 25t plus 300 dy minus 18,900. Set that equals 0 as well. We can see from this first equation here that we only have one unknown t, so we can immediately solve for the tension, which is going to give us T equal to 624 newtons, which is the second part of the problem. And then the third part of the problem is asking for the reaction at C and D. We now know the tension, and that leaves us with one unknown in both equations. Therefore, we know that D of Z is equal to negative 90 newtons, and D of Y is equal to 682 newtons. Just because this is in the J component of the equation does not mean that this dz is the Y component of D. This is still the Z component, and to avoid confusion, that's why I label them like this. So now that we have our D component, we can just make a f of x equation. I'll write that down here, where we have f of x equal to 0. We can also do the same for y, and we can do the same for z. And we now know this value, we know this value, and we know all of our tension values, and we know the weight. That leaves us with 3 separate components and 3 unknowns and 3 equations, which we can easily solve for. And that will give us that when you solve in the C of x direction, you'll get 0. C of y will be equal to negative 454 newtons, and C of z is equal to 630 newtons. And that is probably